Okay, so a very good evening, ladies and gentlemen, and a very warm welcome back to the Grand Salon once again. Now, this next gentleman is one of the world's leading volcanologists. He is a professor at Uppsala University, formerly of Trinity College in Dublin, and he has many, many fellowships to his name. So, ladies and gentlemen, please help me welcome to the stage Professor Valentin Troll.
Thank you so much, Robert, for your kind words, and thank you for joining me. The lecture today is going to be a little similar to the one we had on the Hay Day, where we couldn't go into port, and some of the guests were leaving us in Reykjavik, so we made the call that we would give that lecture because we had so much interest. And today it's going to be similar, but I added a little sparkle because I was visiting the exclusion zone 3 days ago when we were in Reykjavik, and I had my field assistant with me, my daughter Sophie, who is there in the audience, and we had sample permit, and so I'm showing some samples out there. If you're interested, have a look, and I'm going to show you some videos from our little fieldwork day as well. But, well, let's go into it. As you all know, there has been a series of volcanic eruptions on the REYKJANES Peninsula over the last 3 years, and 8 of them have already occurred, and we are anticipating another one any day now, and that would be number 9. And well, before we go into the actual eruption events, let me talk a little bit about why we have eruptions on Iceland. Iceland sits on what is known as the Mid-Atlantic Ridge. This is a large fracture system that spans the entire globe, actually, and it goes through all the major oceans. And in the Atlantic, it goes all the way from north to south. It's a spine, if you will, where new volcanoes are erupting all the time, and the Atlantic is spreading. It spreads at a very, very slow rate. It's about 2 centimeters a year. To give you a flavor, that's about the speed with which your fingernails grow. The Pacific is a proper ocean. It actually spreads a lot faster, with about 7 to 8 centimeters a year. That's about the speed with which your hair grows. So the additional feature on Iceland is that in addition to that spreading center, we also have a mantle plume. We have a heat anomaly that comes from deep inside the Earth, and it pushes Iceland up. This is a bit like Hawaii, and this has been going on for many millions of years. And before the Atlantic spread apart, there was the landmasses of North America and Eurasia. They were together, and this is why we have actually Icelandic lava in Greenland. It's the dark areas there in East and West Greenland, and also in the British Isles, in Ireland and in the UK. But they have been pushed away over millions of years from the center of the activity, which is still going strong, and that is Iceland. Iceland has several volcanic zones that are pretty active, and one of them is the REYKJANES Peninsula. The REYKJANES Peninsula hosts Reykjavik, of course, and it actually hosts 70% of Iceland's population. Well, as you know, Iceland's population is not very large, so it's only 350,000 people, of which most live on the REYKJANES Peninsula. The REYKJANES Peninsula has several volcanic centers, and these are picked out here in the purple colors. We don't need to go into the details of this map, but the Fagradalsfjall volcano is one of these centers, and it's shown here in the little red box. There are several others, and we'll come to the Svartsengi system a little later. And here, the plates are spreading apart, but it's not as simple as they always kind of make it sound in the textbooks. It's not going like this. It's actually going like this. It's a leaky transform fault, as we call it. There's an oblique shear, and when this happens, there's an opening, and these openings, they are allowing magma to rise up. Once magma reaches the surface, it becomes lava. And these episodes of movement, of plate movement, they are episodic. They're not consistent. And it seems that on the REYKJANES Peninsula, there is a kind of geological rhythm. It's different to human rhythms, of course, because time scales are different for the Earth than it is for us and our lives. And here we have a geological sequence. The purple colors, they are eruption episodes of the different volcanoes on the REYKJANES Peninsula. and then we have gaps in between. Over the last 4,000 to 5,000 years, there was 3 major eruption pulses. Eruption period 3 was about 1,000 years before we start to calculate our time, and there were several hundred years of intense activity all along the peninsula, followed by 7 to 1,000 years of inactivity. Eruption period 2 was around about up to, well, our time calculations, and again, several hundred years of activity, followed by inactivity of 1,000 years approximately. And then, round about medieval times, 1000 AD, we had another one of those periods, and then again, 700-800 years of nothing, and now the eruption seems to come back. It seems to actually hold the rhythm. And I'll talk a little bit more about what this might mean in the future. But I think it's not rocket science to conclude that now with 8 eruptions in the last 3 years, we are in for more eruptions to come. So, leading up to the Geldingadali eruption, the first one of the Fagradalsfjall series, it started actually already in December 2019 that there was more earthquakes. And then in March 21, the earthquakes led to intense earthquakes up to M5.6. That's a pretty strong earthquake. From about M4, you have cups falling off the shelves. M5 is quite unpleasant. And then we had an increase in tremors. 40,000 tremors were recorded by seismographs. Tremors is bzzz. It's a shaking, a very consistent shaking. We believe it has to do with gas in the underground. And eventually then the eruption started on March 19th with effusive activity. And here is one of the very earliest lavas that were erupted there on the 19th of March. And it started in the evening of that day in a place called Geldingadali. The early days of the eruption saw a large fracture opening up, a fissure. It was 600 to 700 meters long, and it began to erupt lava. On the 13th of April, 4 new craters formed, so the fissure was starting to develop little volcanoes, if you will, and it wasn't erupting all along the fissure anymore. It's very characteristic that fissure eruptions, they tend to cluster towards single or isolated vents with time. So lava output had been somewhat reduced by then, and certain little volcanoes were starting to develop. So here's a few impressions of the very earliest lava, and there you see the lava spreading on on old ground, new lava on old ground. And if you have moss there, well, the moss starts to burn, so you get moss fires. If you have only soil, then there's no such thing. One of the real issues is actually the moss fires, because they make a lot of very poisonous gas. It's not very good for you to inhale, and this is one of the issues there. Let me give you a flavor from very early days of the eruption in 2021, and here is a little sequence of events. It's compressed, so time is running very fast here, and you will see day and night. Let me get going on this. So you get the idea. The valley is filling up very rapidly. This was only the 3rd night, so this is only 3 days of the eruption, and the little volcano has grown quite substantially, and you see new lava pulses coming out, filling the valley very quickly. You can also see the raindrops on the camera, so Iceland is, well, it's not known for its good weather. And here we see a little bit of snow as well, and this was in spring, of course. And there you can see how the valley gets filled, and eventually the valley spills over because the valley is full and there's outlets on the other side, and then the lava was spilling into other valleys. I think we get the idea now. We shall move on. And here is a little map. Geologists love maps. And here we have the initial crater row, and the craters have little numbers. That's what we do in order to give them a time sequence. And you see on the right-hand side, there was the spilling of the lavas into what's known Meradalia, another valley here. And the craters, that's a very interesting story, because initially, as I said, there was a fracture, a fissure, and here's an impression of the fissure. This was the original fissure very early on, and then the fissure develops these little cones along it, and here we have several of the vents, and the vents will start to be active almost independently then. And the first one is obviously the oldest, the second is the somewhat younger one, etc., etc. So here's vent number 2, and there's a helicopter for scale to give you an impression of what the size of this is. And here is vent number 3. And then we have another impression of vent number 3 here. And this is the crater row with the different vents, and this is from early in the eruption. And there you see vent number 2, and they jump backwards and forwards. And there's a tiny little vent, vent number 5. And vent number 5 was, well, very, very small to start with. And nobody had great hopes for vent number 5, but it turned out vent number 5 was the one that prevailed. So this is a good lesson, and I always teach it to my students. You may start small, but if you are working hard, you can achieve greatness. This is vent number 5 at the end of the eruption. And this was the biggest of them all, and it really towers over all the others. You can see it from the distance. Vent number 5 was really showing the biggest topographic elevation. And let me give you an impression of vent number 5 when it was really going strong. So here you see the fountains coming out from the vent itself, and at the bottom of the vent there's an outlet, and that's where the lava comes out, and that feeds the lava channels, the lava rivers, and they then migrate down into the valleys. So this is vent number 5 on a good day, and let me bring you here into this little sequence, and that is now looking into the vent itself. And I'd like to draw your attention to the top left of that video. Something's going to happen in a second.
Yes. Oh, there it comes. Oh, wow. Did you just get that? Yes.
So you see, my colleagues are talking while I was videoing, but this is a vent collapse, and this is actually quite common because these volcanoes are not very stable constructs. They're building up very rapidly. And here we are. So this is vent 5 when it was super active in summer of 2021, and it started to build a lava pond, a lava lake. The lake itself developed a rhythm later in that year, and this was intriguing, and we studied that a little bit. But here you see the vent is overflowing. When it cools, it develops a crust, but then a new pulse comes through and it's breaking the crust. Nowadays, we don't actually go into vents, we have drones, and here's a beautiful drone image. So here you can actually look into the lake of vent number 5, and it's overcrusting a little bit, but just on the right-hand side, there's a new pulse coming up, breaking through the crust, and eventually this is gonna lead to an eruption. We took a lot of time series images, and this is actually 2 images, one on the left, one on the right, and there's little time stamps there. This is literally minutes apart. So the topmost is 4 o'clock in the afternoon, 4:49, and then it goes down. The vent, the conduit seems to fill up, it overflows, and then it goes down from top to bottom. It's a difference of about 6 minutes or 7 minutes. And then a few minutes later on the right-hand image, 5:04, it starts to build up again, it overflows, and it goes down again. This rhythm was repeated for actually several days, and it was really bizarre. We offer an explanation why that is, and we think it has to do with gas bubbles in there, but we're still not entirely sure. So, spectacular observations, but we don't always have perfect explanations yet. So, the other feature that was happening is we learned a lot about lava ponds or lava pools, And this is not just in the vents, but actually there's lava pools forming outside the vents. Lava piles up and it makes these pools. And the pools can then overflow. And here's a few impressions of some of those pools. And these pools would then build up, they get quite thick, and then they spill out. And this is a little dangerous, these outbreaks, because you don't want to actually be too close if that happens. Once it spills, it's quite likely that lava is migrating into other valleys, and the topography in Iceland is quite steep in many places, and here you get some impressions of lava going down the valleys. Spectacular landscapes, really, really impressive, and there we see that lava might actually run down the hillsides, it cascades down, and this is then spreading out in the low grounds of the other valleys. On the left-hand side is the initial map I shown earlier, and towards the end of the eruption it looked more like in the right-hand side. There we have lava spilling into several other valleys. If you look at the map on the right-hand side, there's the coastal road. It's a very important connection road between Eyrarbakki and Selfoss and Grindavik, and there was concern that the lava might reach that road, but it did not. So there was good news, the road was not cut off. The valley just to the north of the road is called Nathagi, the nice pastures, and this is where people have obviously brought their sheep in order to spend the night, because it was pretty protected. And I'm going to show you a little sequence now of how the valley of Nathagi was filled, and I have a little video here. This is very interesting because now you see the lava is thickening, although there's no flow at the surface. There's likely flow under the surface. So, and there's also gas, and it may actually inflate because of the gas making bubbles. So this is now the Nathagi Valley being completely full. And there's a little bit of rain every now and then. It's Iceland after all. So here is a little impression, and on the right-hand side there is a thickness map, and the different colors give different thicknesses. The blues and purples are the biggest thickness, and obviously near the vents the thickness is on the order of 100 meters and above, and further down into the valleys the thickness goes lower, less than 10 meters. At Nathagi the thickness is very low, and I pointed out the road down there, the Nathagi lavas never made it to the road. Praise the Lord. So this has prevented a little bit of a traffic chaos. However, there was something else going on, and that is, of course, you learn from eruptions, and the Icelandic Civil Protection did several experiments at the time. They were burying all sorts of fiber optics and cables and connection things, and they put them in Nathagi, hoping that the lava will run over them, and then they could test whether the connections hold. Well, the lava didn't make it, as I said, so the experiment failed. And the lesson was unfortunately not really successful, but another important thing that happened is there was experiments with lava barriers. And several lava barriers were produced, several types of lava barriers, steep, shallow, etc. And it turned out that lava barriers do have an effect if the lava is not coming too strong and it's not running too fast. And this turned out to be really useful for the events of earlier this year, and I'll come back to this a little later. Another important aspect is that in 2021, it was COVID. People didn't travel, and one of the biggest revenue sources in Iceland is, of course, tourism. People flocked to the eruption, and there's several claims that the eruption actually saved Iceland from a second bankruptcy. And literally thousands of people came, and the area was rather, well, there wasn't anyone living there, it wasn't very dangerous, so the authorities allowed people to go there. So you have all these YouTube videos where people have sausages on the lava and things like that. I personally think it's a little silly, although I have to admit I tried it myself at some point. So, but then the eruption stopped in autumn that year, and we thought it might be over, but no, it reappeared in August 22 in Meradali, in one of the valleys that was previously filled, and now we had another eruption at our hands. And here's a few impressions now of that eruption. And I'll come back to the lava sampling in a minute. But again, the eruption was very good for Iceland's industry. 10,000 people visited the eruption on the first day. Can you believe that? So people were gearing up, knowing that the eruption might come, and they were ready to go. So the 22 eruption came also with some deformation, and on the lower right-hand side is a satellite image. This is what we do. We have satellites going over the area multiple times. We stack these images. We get these deformation fringes, and that means the area was bulging up just prior to the eruption, and that tells volcanologists something is in the bush. And here's the map in red now on the right-hand side. That's the 22 eruption, the Meradali eruption. And it partly covered the older lavas, partly was also flowing onto new ground. Again, it started as a fissure. And here is the fissures in Meradali. And the fissures were cutting into the hillside. So we had a little bit of activity uphill. And today it almost looks as lava was flowing uphill, but that's of course not true. Lava generally doesn't do that. It was a fracture that opened up. And here in the next image, I'm looking at that fracture with my colleague, and we're posing there. You can see the big volcano, and just at the end of that fracture, there's a tiny little baby volcano. And that's the one on the right-hand side. It didn't become a big volcano, but you can actually study a baby volcano there. So here is the fracture, the original one, and this little tiny little vent here at the very end in the front of the image. That's where this little volcanic spatter cone formed, and there's my boot for scale. And you can actually look inside. It's really cute, I think. And the main volcano was a little further into the lava field, and here is me doing a selfie on August 10th. I couldn't resist. This was just the day I arrived. And you see the volcano is actually not really there. August 12th, the volcano has grown a little. This was not a selfie. Obviously, somebody took that image. And then August 13th, it's grown a fair bit. August 15th, it's a real volcano now. And then this is also August 15th. And let's go on. This is August 17th, and it's now grown into a full-scale volcano. And there's a little overfly video, which I'm going to quickly show you. So the different eruptions then can be mapped, of course. Geologists love to do that. And there were several areas where lava was going onto new ground, but mostly the 22 lava was covering the previous year's lavas. Here's one of the sites where the lava is on new ground, and you see the lava is picking up bits and bobs from the substrate, and you can see chunks of rock inside the lava. And this is one of the tongues, and the vent is just behind that valley there. And this was lava spilling into a new valley. And here is one of those situations as a geologist. This is lava from 21, and you see the lava coming, the 22 lava, and you realize, whew, this might be the last opportunity for getting a sample from the 21 lava from this place. So you rush out and get it, and then you sit down, have your breakfast, and then an hour later, the new lava arrives. And then you take the new lava sample as well, so you get 2 samples in one shot. How convenient. And well, here's another of those places where the lava covers each other, but there's this other phenomenon that is burning moss, and this moss fire is very unpleasant. In 22, this was a really serious issue, and it led to closure of the area several times. And this was where the blue dot is here on the right-hand side. Lava can, of course, come with a lot of force, and the 22 lavas pushed on the 21 lava, and in many places it broke up the existing lava. So here you see broken up lava. This is the pressure from the new lava, and it breaks it up into large pieces. So here is broken up lava, and this is due to new lava erupting on top of it. Just a few impressions here. You can imagine the force behind this to break rock in this fashion. But it's good because you can actually look inside. And here we see the vesicles, the gas bubbles under the crust, and this is how the lava inflates at times. Gas cannot go through the hardened crust, and therefore it starts to kind of push the surface up. Well, geologists love to classify rocks, and we're really into that. So there's different rock types. They're chemically all the same, but there's, because of the eruption phenomena, there's different types of rocks. There's, of course, eruption rocks, i.e. pyroclastic rocks, pyroclastic broken by fire, and there's lava rocks, and there's different types of lava, and we don't have to go into details, but this is, of course, very, very interesting for us to see the transitions between all these different types. The images here on the left-hand side, the lower ones are electron microscope images. There we can identify even the tiny little crystals in the lava, and we can identify all the different forms of lava and pumice. And one really peculiar type of rock came about, and that was the golden pumice. Here is a piece of golden pumice in the field, and it's chemically identical to the black lava, but it's golden in color. It's a stunning rock. Well, people, of course, wondered, how can that be? It's chemically identical, but it looks entirely golden. And the answer is, it's like Coca-Cola. Here it is. The foam on top of Coca-Cola is the same as Coca-Cola, but it has a different color. It's because the light is refracted differently when you have a lot of vesicles in the foamy part, and that's why we have this different color. So that's my best explanation for the phenomenon. So now I'm going to say a few words about lava sampling, and here's a few impressions of the lava. And well, lava sampling requires a lot of experience and equipment. So this is a checklist for volcanologists. This is all the things you should bring. We don't have to go into details, but this is what you kind of bring to the field. But I tell you one thing, it looks great on this image, but when you're in the field, it's very different. So you actually realize, oh, we have to quench this lava. So you're looking at pots and pans and things like that. So here we are looking at the pots that we want to put the hot lava in and cool it. And then when you actually approach the lava, then you realize, oh, where's the wind coming from? How hot is the lava? All these kind of things. Wind, gas, escape routes, all of these things are rushing through your mind, and you have to deal with them. And you need to be geared up. Here's a gas meter, low down, to avoid gas traps. It gives you an alarm if there's too much gas or too little oxygen. And then you have a thermometer here. This is a laser thermometer allowing you to actually get a temperature of the lava. Then, of course, you need to hammer, because you need to, well, hammer the rock. And then you need goggles, because lava can spray, and you need a gas mask. And once you have all these things in place, that's when you can go and sample lava. So when the lava is cold and thin, it's a piece of cake, literally. So here is a colleague of mine and myself taking a lava sample in a thin, open area, thin lava, open area. It's simple enough to hammer it off and label it and put it in a bag. When the lava is runny and it's an open area, it's also pretty good. You can actually scoop it up with a hammer. And here we have a little bit of fresh hot lava on a hammer. The hammer was a bit rusty afterwards, though. So that's the price you pay. If you then want to sample lava inside valleys and the lava is thick, this is getting less easy. You need to actually have a lot more precautions, and you also need to be careful about not causing a fire yourself. And here we're actually kind of terminating a fire, a little fire there in the bottom right image. So when the lava is liquid inside and you are in a valley, it's challenging because you want to avoid causing a lava outbreak from interior parts of the lava field, and you need to get a good estimate for the temperature. The lava needs to be hot enough for a liquid sample, but not too hot so that you cause an outbreak of liquid. So you need to check this carefully, and then once you're confident you can actually sample it, you get ready, and this is us getting ready. And then I'm going to show you a little video of how we took lava samples earlier in the eruption.
I'm going to take a lava sample now. It's a liquid lava sample, and it's going to come from this place there. So let's have a look if this works.
And then, of course, you put it into the little pot and you cool it, and then you can bring it to the laboratory. So, and you do this many, many, many times over the course of an eruption. It's almost a daily effort, and then you get these lava rocks that are still kind of warm, and then you back them up just about the right temperature that they don't melt the plastic bags. And we did this for hundreds of samples. So here's all the different sample sites of the lava field. And on the right-hand side, just to give you a flavor, is the geochemical data we are producing from that. And the interesting news is that the chemistry of the lava was changing throughout the eruption. If you're interested, we can talk more about what that means. It's maybe not the most important thing for this presentation, but the chemistry changing is, of course, scientifically very, very important for us to understand. So eventually we came to write our little paper on the initial eruption, and we thought it was all over. This was published in June 22, but, well, no rest for the wicked. A few weeks later, the eruptions continue, and the next summer we had another eruption, the Little Eruptor eruption. And here we have a little map on the right-hand side. The gray is Geldingadalur 21, Meradalur 22 is in blue, and in red we have the Little Eruptor eruption. The vents shifted north, and eventually the three lavas actually met. So here is an impression of the Little Eruptor vent and the lava field that was emerging from there. The lavas were traveling south, and here's the vent area, and this is actually a video. So on the bottom right, you can see a colleague of mine taking a picture, and you just see a little bit of lava fountaining. But if you take a drone and fly over this, inside the vent, the world is very different. So what looks like a tiny little fountain coming out is actually a boiling lava lake inside. So the Little Eruptor eruption saw another major change, and this was really a game changer. And this was, we got these protective suits. And this was a donation by a steel manufacturing company, and they have been a game changer in the sense that, well, the sampling is still the same, but suddenly there was a huge interest on YouTube. So the suits look really cool. So, and some of our videos got literally tens of millions of views, and we got famous for that. So the technique is actually the same. We still scoop the lava up, but it looks a lot cooler. So, and a few impressions from Little Eruptor 23. Here is the new lava running over the older lava. So the new lava approaches in 23, running over the 21 lava here. And eventually we have lava fronts coming in. So here's a lava front running over new lava. And here we have this wonderful situation. I'm standing on 21 lava. The 22 lava is visible to the left. It's the dark layer on the left. And then the 23 lava comes in from the right. And eventually these three lavas met. And there's one place in Meradalur where all the three lavas are lying on top of each other. And, well, we couldn't resist. We had to go there, and look at us. We are kind of triumphant here. This is the place where all the three lavas are stacked above each other. And just a few days ago, 3 days ago, I took my field assistant with me, and we had permit to go. And here is my field assistant, Sophie, my 16-year-old daughter, who is with me on the trip. And where it says Volcano parking, that's where you should leave your car. But of course, we drive on. And Sophie is a very experienced field assistant because she was helping her dad already at a very young age. So here she is, a 4-year-old in San Francisco at a convention. And there she holds a tiny little piece of a Martian meteorite. You can see she's clearly impressed. Well, I'm not sure. But, so here, Sophie is with me in the field there, and there we are looking at the 21 lavas, and I think this should work. So, this is Sophie for scale, and the 21 lavas are still a little warm. That's the wind, it's not the volcano, I'm afraid. So, and Here's a few more of those impressions, and there's a beautiful shot on the left where you see the 22 lava flowing into a crack of the 21 lava, and there's a few more little video clips. They're all very short. Let me run them quickly. So here is still gas coming out, and Sophie used the opportunity because it was pretty cold, and if you put your hands in the crack, it gets actually quite nice and warm. So now, having looked at the 21 eruption, I need to say a few words about hazards. And hazards and vulnerability, that is what makes disasters. It's an interesting concept that people talk about natural disasters, which is a no-no in the scientific world these days, because disasters come about from us being a little silly with things. And it's actually that nature does what nature does. It's us who are putting ourselves in the way. And this is where bad things happen. So the eruption started off in 21. It was quite a remote place, but it was already obvious back then that there is some vulnerability spots. I pointed out the coastal road in the south of the lava field. You can see the lava field on the right with a little volcano orange dot. But there's also the town of Grindavik, and there is the Svartsengi power plant and the Blue Lagoon. You can see this turquoise little area there in the upper left-hand red cycle, and that is the Blue Lagoon and the Svartsengi power plant. So the other thing that was early on identified as a vulnerability spot is the Keflavik airport, because the Svartsengi power plant actually supplies all the electricity and heat, the hot water, for Keflavik airport. And without electricity, it's hard to run an airport. So this is the largest of the airports in all of Iceland, the only big, really seriously big international airport. And if that wasn't operational, it would be tricky. People ask very frequently, is there problems with airspace? Is there problems with air travel, like in 2010 with Eyjafjallajökull? And the answer is no. It's a very different type of volcano. There's a little bit of gas coming up, but it's a rather low cloud. Airplanes can fly around, no big deal. Sometimes you get condensation. This is not an eruption cloud, this is a condensation cloud. The eruption cloud is almost not visible, but it brings a lot of gas and aerosols, little molecules, and then you get water condensation, so you might have a condensation cloud. That is not a huge problem, even if an airplane would go through that. But one thing that the Icelandic colleagues and, of course, all the other volcanologists have identified is if the eruptions continue, there may be problems for the larger infrastructure and the larger traffic situation. This is a very complicated map. It looks at all the rocks there, but I'd like to point out, draw your attention to the pink rocks. The pink rocks are the lavas of the last eruption cycle from medieval times, and these reached the south and the north coast, and that means both highways in the northern part and the southern coast would be at risk if eruptions continue and there's more lava coming out. And in the bottom image there is a big aluminium smelter. And the aluminium smelter is, of course, a very useful thing because cheap energy in Iceland allows you to smelter aluminium ore. There's no aluminium ore in Iceland, it all comes from India. But the energy situation is very advantageous there, and therefore you can do this. And let's see whether I can get this pointer to work. Here we are. And the aluminium smelter sits right here at this point where the arrow is. And well, if there's more and larger lavas, the aluminium smelter may actually be at risk as well. Should one of the highways be cut off, we're having the problem of the airspace or the airport not being particularly useful. There's two other larger airports. One is in Akureyri, where we've just been, and the other one is in Egilsstaðir. Unfortunately, both of them are far, far away from Reykjavik, where most people live. So this is going to be very challenging, and an air bridge will be potentially very difficult. So from an infrastructure point of view, there will be some head scratching ahead. So this was all about the situation 2021 to 2023, but then the volcano played a trick on us. It shifted its activity towards the west. and it did so just before Christmas. I just came back from the annual American Geophysical Union meeting, and I land at the airport in Stockholm, and I look at my phone, and it had started. But it had started 7 kilometers towards the west in the area around Svartsengi, just next to the power plant. And a new volcano started there, and it erupted very frequently over the last few months. And here on the right-hand side at the bottom, we have the swelling, the deformation in the different colors, and the whole area round about Grindavik and Svartsengi is being pushed up, and it erupted. Well, the lava was moving towards Grindavik, and barriers were put up really, really quickly, but one of the fissures opened up inside the barriers, and there's nothing you can do, and it hit the town of Grindavik. Several houses got destroyed, they were burning. This is going to be a video now from April this year, just to give you a flavor. The Svartsengi lavas are quite runny, actually. And here is an impression of lava close up. So it gives you a flavor for how fast lava is generally moving. And while you can walk away from it, it's unstoppable. And within just a few months, we had a large lava field developing, building up at Sundnukur. And Sundnukur is the crater that then developed. And there we have the Sundnukur lava field. This map is already outdated because it doesn't have the June eruption on it. The lava has progressed further towards the south and further towards the west by now. And you can see the two lava fields, the 21 to 23 and the 23 to 24 lava fields from the different sides. So they're not super far apart. And yeah, unfortunately now the eruptions are of the same nature, but they are affecting infrastructure and population centers. So the Icelanders have experimented early on with the lava barriers, and they are pretty successful. The map on the right-hand side in red, there's red lines. It shows the lava barriers, and you can see the lava was flowing around Grindavik. The lava barriers are pretty high, and they have gaps in them for the roads, and they can close the gaps within an hour or two. There's a whole fleet of caterpillars and trucks on standby, and these lava barriers have proved enormously efficient. The Grindavik situation is less pleasant, and this is images from just a few days ago. So here we have lava incursion into the village, and some of the houses got swept away by the lava. And here, well, this lucky chap had a fence that was able to withstand the lava. I would market that if I was him. But of course, this is sheer coincidence. So the lava was just running out. And this is footage from just 3 days ago. So here is a lot of fractures that opened up. Here's one of the houses that got bent. You can really see the bend in the house, and there's Sophie for scale. Other houses got fractured, and this is actually a little video. Let me show you. Hello, I'm here in Grindavik, and I'm just looking at the various damages. We have it July now, 24. This is from earlier this year, and here you see the road has been filled in. The crack that went through the road has been filled in, and there is a metal bridge over it now. But the cracks continue, of course, beyond the road. These are cracks that come due to dike intrusion, but also due to tectonic movement. And there's a building here, and of course the building is affected as well. So here you are, a big crack in the building, and over there is another one. There's a few smaller secondary cracks here as well. Let me get a little closer. Well, I think you get the idea of the cracks here, and this is, of course, a very serious concern. The Svartsengi power plant is supplying not only the airport, but also Grindavik, and Grindavik is now evacuated, and here is a drive-by video of the electric power cables. Hello, I'm here just outside Grindavik, and we are just passing one of the electricity poles that was taken down by the May to June lavas, and here you can see it. So the pole is still there and the cables, and yeah, we're driving by. We're not allowed to stop on the road here, so but you can get the idea. So the lava has dismounted this one, and the cables are still kind of there. They have fallen onto the lava, and of course this is no longer active at this point. So, and this is the youngest lava in all of Iceland, and there's a specimen over there, and here's my field assistant Sophie for scale. And there's one of the vents in the background. You can just about see it. It's still producing a lot of gas. It's still steaming, if you will. And you can also see that the lava was pushing the soil up the hill. So you can really see that little dam of soil that was pushed up by the lava. It comes with quite some force. And here's a little video of the vent, and I can go a little closer. And this is probably going to be the vent that will erupt again, should it come to an eruption in the next few days. And this is the lava itself. So this is the beautiful lava that we sampled. This is the outcrop, the place where the lava specimen that I have on display is coming from. And I'll skip the video, but if you kind of look into the holes, there's still a lot of gas coming out there. So now a few concluding words towards the end. Here is the Svartsengi power plant and the Blue Lagoon, and in the background you see the Grindavik Road. The Grindavik Road has been overrun by lava 3 times already. The Icelanders are really good. They can actually build an improvised road within 2 days. So they are not very nice roads, but they work. And the issue is that the eruption sequence seems to kind of get more rapid now. Here is the different events in a timeline. The timeline is consistent, and the scale here is consistent, and you can see the Sundnúka eruptions, they have become really rapid. Quick succession of small eruptions, and as I said, we're expecting another one very soon. And this lava road phenomenon is quite intriguing, and here's a little drive over the lava road, and this is from just a month ago. You're not allowed to stop, and you don't want to be in a traffic jam there either. So that was that. Enough excitement. Let's talk about, for 2 more minutes, about what the new eruption might look like. And several people asked me, how can you actually predict that there's an eruption happening? And well, we see the swelling of the land, and the swelling allows us to make a little calculation of how much magma must be underneath the volcano. So the more swelling, the more magma there must be. It's not rocket science. How you calculate it might be rocket science, but the concept is simple. And here we can use that calculated magma volume and the days of the swelling, whenever the swelling starts. And on the left-hand side, you see different swelling episodes over the last half a year, and many of them lead to an eruption. Each of the stars is an eruption. Each of the squares is a swelling episode that did not lead to an eruption. Sometimes that happens. The current situation is the red line. The circle means we have no eruption yet, but it's swelling, and the swelling has already overtaken some of the previous eruptions. So this is a status from about 10 days or so ago. And here on the right-hand side, in the top, you see the swelling, and the swelling is larger already than it was in the previous eruptions. Let me bring that here. So the swelling is already, so, oops, it's very hard to get this arrow to the right spot. Here we are. So this is where we are right now, and this is again from about 10 days ago. So the swelling is likely a little higher now, and that means we are at the brim. The magma reservoir is full. And just today, the Iceland Met Office released this statement here: continued increased probability of another dike intrusion and volcanic eruption. And in the small print, it says it'll gonna happen very, very soon, most probably. So, luckily, we are here in the safest part of Iceland. The rocks here are very old. We didn't have any eruptions here for about 14 million years. So all is good and we're leaving as well, so it's all right. But one question I also get, that is, how about Reykjavik? Is Reykjavik in peril? Well, this was a good question, and one of the scientific editors from one of the major journals asked me, Val, can you say something about this? I met him in February and I said, yeah, I can try to work on this. So he invited me to write an article, and so we just published this a month ago. And here we put up these 3 hypotheses. They did little diagrams to the bottom. C, D, and E is the 3 hypotheses of how the subterranean magma field might actually look like. There could be a larger reservoir below the crust at the top of the mantle. There could be many small ones, and there could be one large one that spreads throughout the entire peninsula. The right-hand one would be very bad. The left-hand one is not very good. The middle one would be the best of all outcomes. Now, the good news is, oops. Oh, this is letting me down. No, the good news is the magma chemistry is identical. So we don't have a new volcano. It looks to be a small situation. It looks to be a small volcano. And this one is not coming up. I don't know what it's doing. Let's try to get out of here. Sometimes it works better if we are not in projection mode. No, it doesn't work. Unfortunately, it doesn't show up. Oh, here it is now. Super. So, and this is a seismic tomography. It's like a CT scan, and it shows that there is a magma reservoir at about 10 kilometers depth, and luckily, it's actually not that big. It's sufficiently big to cause eruptions, but it's not huge. So, if we want to kind of come back to my 3 hypotheses here, it is indeed this option that seems the most likely one, and that is actually good news. We can stay positive. So there is no magma under Reykjavik itself for now. And this means that Reykjavik should be safe for at least some time. But the other reality that geologists have to point out is ultimately, if this is anything to go by, there will be more eruptions in the area. And there is now 2 systems that are active, Sundhnúkur and Fagradalsfjall. And if the others wake up as well, we may be in for one of those major eruption periods that could last hundreds of years and could produce many, many small eruptions. So that's the reality we are facing, and it's time to get ready for that. So I'd like to say thank you for your attention. And well, join me tomorrow if you like, because there I will talk about the good sides of volcanoes, because they're not all bad.
Ladies and gentlemen, Professor Valentin Troll.